Today I'm going to present my PhD about the hydrogen fuel aircraft configuration and trajectory optimization to reduce aeronautic environmental impact. As you may know, aviation is a contributor to climate change, and this is going to get worse due to the increasing number of flights. So this has triggered the urgent need to reduce emissions to meet the climate goals, and we need to also take in place quick and disruptive measures. We can divide these measures into three blocks, starting from technological ones that are mostly carbon dioxide oriented, could be alternative fuels, electrification, hybridization, all the advancements in drug and consumption reduction. And also we have the operational measures that is mostly flight planning that are non-CO2 oriented, I will explain later. All of these coordinated by the policy-based measures that we can also apply. As you may guess from the title, we're going to talk today about hydrogen. So in the graph in the right-hand side, you can see all the species that are contributing to climate change from aviation, carbon dioxide, and all the non-carbon dioxide ones. Basically, including hydrogen in the propulsion part, we can get rid of directly the carbon dioxide emissions, but we need to take into account the increase in water vapor and the potential increase in contrails that is also playing a role. So even up to 2/3 of the current impact. But a good part is that mitigation of these non-carbon dioxide effects has been promising through operational strategies due to the strong dependency on time and location of these emissions. So we found out that if we join both efforts from the operational trajectory study and the research and design of these hydrogen aircraft, we can both tackle the known CO2 and CO2 emissions, so rounding off the problem and maximizing the benefits of the introduction of the hydrogen airplane. I present here this schematic of my PhD with the general objective of analyzing the introduction of this aircraft, quantifying its climate impact reduction into the market. And the sub-objectives divided in three blocks that basically goes from the design, analysis, optimization of this aircraft, the climate modeling and emissions, and the climate optimal trajectory planning algorithms. So starting from the design part, it is clear that we need tools to predict the feasibility and also the capabilities of an aircraft in the design part. Obviously, this is even more critical if we don't have previous expertise or knowledge in this novel concept. So this is when design analysis and optimization comes. That is basically formulating this design phase into an optimization problem with the objective of being cost, emissions, impact of weight to reduce it by varying these design variables that could be geometry, sizes, and power ratings of the different subsystems of the aircraft, subject to the constraints that could be the mission, airworthiness, or basically physical feasibilities of the aircraft itself. After a brief state-of-art of the works done in conceptual design of hydrogen aircraft recently, this is not a kind of novel problem, but has arised a lot of interest in the recent years due to climate concerns. We can see that there are several works focusing on different parts of the system of the aircraft, but none of them has proved that, well, has arisen as a complete model, also all taking into account the specific requirements of hydrogen, taking into account our airworthiness for a quick introduction into the market, and also computing the impact of the aircraft itself. This is why we modeled this platform presented in this conference that is basically doing the multidisciplinary design and optimization of the hydrogen aircraft, giving us an input and specific mission that the aircraft needs to fulfill, and basically involving all the subsystems of the aircraft, the propulsion, the thermodynamics of the tanks, the stability, also the kind of monitoring, and also taking into account all the changes that we can apply in geometry, in aerodynamics, and in stability, so being able to find the best solution, the optimal one. I'm going to present you this test case that I presented in a couple of months ago. That is basically modifying an i320 Neo for the use of for a hydrogen propulsion system. Basically, the key here is to allow the stretching of the fuselage to allocate the big cryogenic tank on the fuselage itself without setting a huge penalty on the space for the cabin, meaning the payload, not even restrictions on the weight and the space for the payload. I performed here an optimization campaign in all these different ranges and payloads, comparing the conventional to the hydrogen retrofitted aircraft. Basically explain the results. Obviously, for carbon dioxide, we can achieve up to 99% reduction in operational, in total, both accounting for operational emissions and manufacturing emissions, depending only up to 70%, depending on the manufacturing process of the hydrogen itself. Also, going into numbers, if we compare the fuel consumption in energy terms for a fair comparison, meaning that we are multiplying the low heating value of each of the fuels, we can see that we can achieve around a 15% reduction, more than double the price of the fuel itself due to the high cost of hydrogen. We also have a huge increase in water vapor and a reduction in NOx following this method that's taking into account internal conditions in the turbofan. Talking about the sizing, we can see that the plane itself is being stretched, is getting longer as soon as we reach higher payloads in order to have a space for both the payload itself and the tank. And also that the wing is being shipped afterwards to compensate this increasing weight on the back part of the plane without losing stability. I didn't include here results for the double tank configuration because they were not really relevant under the selected optimization problem. So the next question that arises here is what to do with all this increase in water vapor. So basically, we will get into the contrail analysis. We need to understand contrail to fly this hydrogen aircraft, but the contrail is still subject to huge uncertainties, and even the hydrogen aircraft, the hydrogen contrail has not been nearly addressed at all. So I show you here a review of the current models that could be useful for aircraft trajectory simulation. Nearly only one of them is starting to include capabilities for including hydrogen aircraft, but we still have a huge number of uncertainties, and we still need particle emissions input to run. There have been also recently new high fidelity works and approaches for computing different parameters of the hydrogen contrail. They are more high fidelity and focusing one of the phases or just one of the key performance indicators. So from this review, the main concerns are that we still lack for a model or data for particle emissions, and this triggers the lack of both reliability and applicability of these models. So redefining this second objective, we need to adapt any of these current models for hydrogen, or basically make any of these high fidelity ones useful for aircraft trajectory simulation and optimization. From this second part arises the idea of this project that I did in collaboration with Stanford University, that basically joins an effort of taking results from a 3D solver simulation and compare them against cases that we could see from the ground camera images, with basically the goal to understand the predictability and the limitations of these kinds of models and comparing it against current platforms that are being in use. I presented this work in EGU just a month ago. That basically was selecting each of these visible flights and running it on both the ILS and in COSIP, that is the benchmark model used here. And the results were not very very concluding, because it resulted that both the models had the same problems and limitations. We basically thought that it was because of the errors and uncertainties in both the aircraft and the meteorology data itself. So yes, I mean, less simulations and ground camera can be a good solution. I mean, a good approach for having a better understanding on control formation, but still lots of work is needed, and even more for adapting this to hydrogen. Going to the last part, trajectory optimization. So basically in trajectory optimization, we try to solve this kind of problems. We try to solve this objective function or performance index in order to reduce time, cost, or emissions or climate impact. Also regarding the dynamical model of the aircraft itself and the path and state constraints. So ways to solve this is one of them is optimal control. That is basically solving the dynamical optimization itself from two different approaches. That would be direct, discretizing the trajectory and solving as a non-linear problem, or indirect, basically analytically solving the problem by the point-Graham model. So, and also, well, we have here non-optimal control. I'm gonna quick, yeah, I know. After a state of part, indirectly the climate optimal trajectory optimization, we can see that the hydrogen trajectory optimization is completely missing. But luckily, we have our in-house libraries, both ROC and RUS for free routing and structural space, that we can adapt, introducing the models beforehand presented from hydrogen and climate impact. Just some test case, optimizing both fuel and time in this flight, comparing conventional aircraft to the hydrogen one in this design from the results presented before, and in 3 different takeoff weights. So from the result, we could see that for this case, the hydrogen itself, it will be flying higher at a higher speeds too, obviously with a bit more of drag and a bit more of thrust, and also the difference in the weight evolution and the fuel consumption. Also with a slight difference in the lateral path, mainly due to the changing altitude, so the changing winds. This is the main result that basically align in total terms with the ones presented before, with increasing cost, reduction in carbon dioxide, and also a slight reduction in energy. So the next step would be to finish the journal paper about multidisciplinary design optimization of the hydrogen aircraft, improve the work presented in EGU about contrails and ground cameras, and also to start to incorporate the climate models into the trajectory optimization part. So not only optimizing for cost and time, but also for climate impact. And that was all. This is my contact, and also some achievements that are my research estate, the journal papers, and the conference papers. Sorry for the increased time. Thank you.